Shimura Varieties and the Bernstein Center.
Okay, thanks very much for the invitation to speak. I should apologize to the experts in the audience because this is going to be a sort of a colloquium style talk, at least for most of it, as I was instructed. So let me, most of the talk's going to be about representations of p-adic groups. And in particular, there's basically two ways, I'm going to compare two ways of thinking about parametrizing them. So one way is local Langlands correspondence, and the other way is the Bernstein decomposition. So I'm going to assume that people know what a p-adic group is, but I'm not going to assume you know much about these correspondences. I'm going to describe them or at least review them. So I'm going to put an outline here. So first, notation. Second, local Langlands correspondence. Third, Bernstein theory. Then, so to speak, main point is that we want to construct a map from the representation ring of the dual group to so-called Bernstein Center of the p-adic group. So I'll say what I mean in a second about that. Then I want to state something called the test function conjecture and say what is known about it. And then in the last, if I have time, I will talk about endoscopic transfer of the Bernstein Center. Okay, so throughout this talk, so F will be a p-adic field, or if you like, it could be a function field, the local function field. And so we'll contain its ring of integers and a uniformizer. And well, we'll be considering the Weil group. So the Weil group will be denoted this way. So it's a group that fits into an exact sequence. In other words, it has the inertia subgroup called I sub f. And then, well, that maps to Z. And so inside here, there'll be some special elements we call geometric Frobenius. So that's just the inverse of an arithmetic Frobenius. And we're going to be considering G is going to be a linear algebraic group, a connected reductive linear algebraic group. Usually I'll write it that way, but I'll actually shortly stop writing the underline. So G will be the F points. And like I said, shortly I'll just be writing G instead of this. G instead of, well, I'll stop writing the underline. And let's assume, for simplicity only, that G over F is split. This is not necessary, but it makes things a little simpler to state. And let's assume that we have, let's consider the dual group. So this is a group over the complex numbers. So in this split group, we can consider a torus. So consider a split maximal torus T inside G. And the usual thing with the dual group is that we consider co-characters of this torus to be the same as characters of the dual torus. So for an element that is in this co-character, we'll simultaneously think of it as a character on the duals. That means that co-characters of the group can be thought of as weights for the dual group. Okay. Here's a baby version of the things that I want to talk about in some sense. It comes from local class field theory. So I can consider smooth meaning locally constant characters from T of f to C. So this is with respect to this means that in some sense you can just give this the discrete topology and consider characters which vanish on some compact open subgroup. And there's a one-to-one correspondence between those things and homomorphisms from the Weil group to the dual torus. And I mean, for example, this just comes from, if in case of T being just the split torus GM, everybody knows this. I mean, this is, if you take a character, you can associate to it the map, which using local class field theory, you can identify its abelianization with f, and then you can compose here. So this says that to a character here, you can get a homomorphism to this, and this is thought of as the dual torus of GM. Okay, so this is just local class field theory that you can do that. And because the torus is split, it very easily you can derive this statement from this. Now what I want to do is say, well, we should think of both of these things as algebraic varieties over C. And how would you do that? Well, you can think of them as homogeneous spaces under, or as a union of homogeneous spaces under T hat. Namely, well, so this set of things carries an action of the set of all unramified things. So you can look at the maps from this modulo of the inertia. And that's just isomorphic to, say, the group generated by this Frobenius. So you can look at maps from there into there, and you can just pointwise multiplication gives you an action of this on this. But these things are just determined by the value of this geometric Frobenius. So this, of course, is just isomorphic as a group to just T hat of C. I'm just writing the C to emphasize that this is a complex variety. On the other hand, on this side, there's a similar thing. You can take a character and you can twist it by an unramified character. So this, you can look at the unramified characters, T of f to C star. And those things are also isomorphic to T hat of C, so as is well known. And so so you could think of this as an infinite union of copies of T hat. Okay, so now let me just remind you, not that anybody needs to be reminded, but it's a statement of local Langlands classification. So this is, of course, a conjecture in general. So I want to just say what we expect in general. The local Langlands correspondence says basically that there exists a finite to one map satisfying some properties, which I won't write down most of them, but write down one of them, from so irreducible smooth representations pi of G of f to certain, I call it admissible, homomorphisms from the Weil group, from the Weil-Deligne group into G hat, modulo G hat conjugacy, where this is the Weil-Deligne group, and I don't really need to remind you what it is because it doesn't really come into this talk, because there's another finite to one map from those to just, when you restrict such a thing to just the regular Weil group. So the Weil-Deligne group is something bigger than the Weil group. But I'm going to just restrict, so I just look at maps from the Weil group into G hat, again modulo conjugacy. And so this is there's a finite to one, there's supposed to be a finite to one map. And so if I take a representation here, I should associate to it something, I'll put a prime there. And then I associate to that this thing, which is just the restriction of that parameter to the Weil group. Okay, and so this is supposed to satisfy numerous properties. Of course, for GLN and some other cases, it's known that there exists this thing, and in fact for GLN it's a bijection. But, well, I should say this arrow is a bijection. But one of the properties that at least I haven't seen stated explicitly in the literature that should be true is compatibility with parabolic induction, normalized parabolic induction. So I want to say what that means. So so this is normalized in the sense that we're taking normal parabolic induction from a representation of a Levy factor of this. And when I write these, I mean f points in some sense. I'm going to, again, start abusing notation. Here, this means f points. So I have a supercuspidal representation of m of f. And I just can take the usual parabolic induction, but there's a normalizing factor coming from the modulus character of p coming in. And if the compatibility is the following sense. So if pi is a subquotient of this thing, then, well, you can consider the parameter where you've restricted to the Weil group. So that's a map from here like this, and it's only defined up to g hat conjugacy. And you can also consider the corresponding thing for the representation of this group M, and so this parameter should go into M hat, which of course is included in a non-canonical way in G hat, but it's well defined up to G hat conjugacy. And these two things should be G hat conjugate. So we want this property to be also true for the local Langlands correspondence. So, for example, so make a remark here. So the trivial representation, just to illustrate what's going on, I mean, the trivial representation and the Steinberg representation for GL2, so these things are both constituents inside So this is the modulus character, and you take the minus 1/2 power. You look at this. These two things are both in there, but they have the same phi sub pi. Of course, they don't have the same Weil-Deligne parameter, but they have the same thing when you restrict to the Weil group. And the other thing is that, well, okay, so what's known about this? It's known for GLN. Or GLDs. And it's basically, this is the Bernstein-Zelevinsky plus some calculation of Jacquet. Tells you that that expectation over there for compatibility is indeed true for GLD. And for other cases, I don't really know. But it should be true. OK. So now I'm going to switch to discussion of the Bernstein theory. I'm going to remind you what that says. So Bernstein theory, we start, again, we're going to abuse and say G is this locally compact group G of F. And associated to that, we have the Heck algebra. So that's, well, I mean, in concrete terms, it's locally constant functions on G of F with a product convolution determined by some choice of Haar measure. But if you don't choose the Haar measure, you can just think of this as the convolution algebra of measures on G of F, complex valued measures. And we have another algebra, which is can be defined this way. Most concretely, it's just the inverse limit of all the centers overall, so all the compact open subgroups, J. So J is always a compact open subgroup of G of F, and I take the center of the Heck algebra of biinvariant functions, J biinvariant functions on G. So that's that symbol. And what do I mean by compatible? Well, it's easiest to state if you think of them as measures. So take a function, take a family of a system of measures where J ranges over these compact opens. And this measure is, by definition, just the one that the Haar measure that gives J measure 1. And so we require that if if j prime is something smaller than j, then we have to have the following compatibility. You can multiply by another measure, and this is the idempotent. So this is ij, where this is the characteristic function of j there. Okay, so that's a compatible system of things. These form such things form an algebra under multiplication, or convolution. And it's not exactly contained in here. It's contained in some completion of this algebra, the Heck algebra. But it's the center in a certain sense. And in order to say what that is, I have to remind you what the Bernstein decomposition says. So roughly speaking, there's the category of all smooth representations of G of F. It decomposes as a disjoint sum over some connected components of the variety of supercuspidal supports. And these things are sometimes called blocks, or Bernstein blocks. So to say what that means, so what is a supercuspidal support, and what do these components really correspond to? Well, so if you take an irreducible smooth representation pi, so that's automatically admissible, and so you take some irreducible representation, and you can embed it. There's a subquotient. It's a subquotient of something of the following form, some normalized induced representation. For pi, sigma is a supercuspidal of m, which is a Levy factor of this p. And the conjugacy class of the pair is well determined. And the map from pi to this pair is finite to 1. And so we call this G conjugacy class of these pairs, we call that the supercuspidal support. And we want to group them together in some kind of algebraic structure. So what we notice is that if you give me a pair like this, I can take any, I can act on such pairs by just multiplying, twisting these supercuspidal representations by unramified characters of m. So, so what I do is I say, well, I'm going to consider the following set of things. So it's pairs of this form. An unramified character of m of f. And so in other words, it's in something you could call this, which is equal to some complex torus. So in other words, what I'm saying is that you just consider the set of all these things, which obviously carries an action of this torus, and it's a homogeneous space under it. And you consider all such orbits, and every orbit gives you the structure of this thing modulo some group. So basically, you get this thing is equal to a complex algebraic variety. And the set of all supercuspidal supports is just the disjoint union over all the possible orbits you can form this way. And the ring of regular functions on that is going to be the product over all the corresponding rings on these. These are some affine varieties, and you just take all of the corresponding rings. So you get some ring of regular functions on the variety of supercuspidal supports. Of course, what this decomposition that I wrote right here is a theorem. It basically says that as categories, that these consist of the representations, say, the irreducible representations in this category are the ones that would belong to the induced representation of something of this form. And the theorem is that there are no morphisms between things that belong into different blocks. Okay, and this ring is another theorem is that this ring can be thought of as this other ring called the Bernstein Center over there. So that's a non-trivial result. So let me state it. Oh, before I state it, let me give you an example. So one kind of common block that frequently comes up is something called the Iwahori block. So for example, one thing you could do is you could take your levy could just be the split torus T, and you can consider the trivial character on that. So all unramified characters times the trivial characters, just saying that you're taking all possible pairs of the torus and an unramified character on the torus. And if you look at the corresponding block, you get something called the Iwahori block. So if S is the Iwahori block is equal to the case where, yeah, well, let me write it this way. And so it's a well-known thing that the things in the block are exactly the unramified principal series. Okay, and okay, so here's a theorem of Bernstein. So it just says that an element in this ring here acts on an irreducible pi by a scalar which depends only on the supracuspidal support. And it varies regularly as you vary pi. So it determines a regular function. And moreover, the resulting map is an isomorphism. So z goes to the function determined by all scalars as you vary the pi's. All right, and moreover, this thing is equal to the essentially compact g-ad invariant distributions on here. And I won't exactly say what that means, but what it does mean is that if you take a z and you can convolve that with any function, so a distribution can be convolved with any function that's compactly supported, and what it says is you'll get another compactly supported function, and in fact it will be z sub k if z is represented by a family of this form. So in other words, if I write my element out this way, then this operator, all it does is project onto the kth place. So that's important to keep in mind, because what we're going to do is have functions that arise abstractly as functions on the regular thing, and then there's going to be some abstract way by virtue of this theorem to write them this way, and the projections will be gotten by just doing this abstract process. But these projections are the things that we're interested in. All right. Okay, so now I can go to the next topic, but before I say about this next arrow, I just want to say, I mean, in general, it's a question that's pretty much open, is exactly what is the relationship between these two parameterizations. So on the one hand, you have the local Langlands correspondence. So if you give me a pi, I get some kind of parameter over there. And on the other hand, if you give me a pi, I get some point in some variety, namely in the variety of supercuspidal supports. And so I get 2 points in different complex varieties. And we could ask, what is the relationship between these two things? And it's not really, I mean, so it's difficult for, one reason it's difficult is that in general, like not for GLN, but for groups like GSP4 and other groups, a single L packet can contain representations that are, say, have Ewell-Horry fixed vectors and other representations that are supercuspidal. So in other words, what that means is that an L packet can cross several different Bernstein components. It can hit several different Bernstein components. Okay, so what it suggests is that, and another thing I should say is, well, and so the Bernstein Center is something that acts by scalar depending on things in the supercuspidal support. If an L packet is going to meet several different Bernstein components, it suggests the definition of a smaller ring inside the Bernstein Center called the stable Bernstein Center, which is the things that would act by the same scalar on all the representations in a given packet. And such a thing has been proposed to exist. Of course, it can't be proved to exist unless one knows local Langlands, but it has been proposed to exist by Vogel. And it turns out that the functions that I'm about to describe will lie in this smaller, stable Bernstein center just by construction. Okay, so what is this construction? So I want to explain how, if you give me a representation of the dual group, and by that I mean that's actually the representation ring of the dual group over there, I want to construct from it in a canonical way something in the Bernstein Center, and I have to assume local Langlands conjecture to do that. First, let me motivate it, though. I mean, so we're going to start with a representation in the dual group. So this means just finite dimensional algebraic representation of G hat. And remember that if you have a Weil-Deligne parameter, you get this restriction to the Weil group. You also get this monodromy operator n. Okay, and recall what is the definition of the L function associated to a pi and a v. So we assume that pi is irreducible again. And if we take the log of the L function of pi with this representation and a complex parameter s, then that's going to be the sum for all r greater than or equal to 1 of the trace of our parameter attached to this rth power of Frobenius acting on, so now what does it act on? Well, it acts on the kernel of n, and then you take the invariance under the inertia group. And then, of course, you have some kind of sum like this. But these are the crucial things here. Now, the theory of bad reduction of Shimura varieties leads one to consider something different because of one of the fundamental stumbling blocks is that we don't, on the cohomology of things like Shimura varieties that might have singularities modulo p, you don't know well enough how inertia acts. So it sort of makes sense to, it turns out that the correct thing to do is to consider a semi-simplified version of zeta functions, which I'll remind you about in a little bit, but there's also the semi-simplified version of these automorphic L functions. And so what those are is you just write down the same exact expression, but here, instead of the kernel of n, you just write the whole space. And everything else is the same. So in other words, what this suggests is that that you should be, well, let me write this part out. So you should be considering objects, numbers like this, and we just give this a name. We call this the semi-simple trace of this power Frobenius on V. So that's just a definition. Okay, and Well, the proposition is just that if we assume things like local Langlands correspondence and yeah. I mean, what I mean here is just this factor is replacing this. I mean, the rest of it's the same. I mean to write, I didn't write it, but I mean, I meant to write these and indicate that these things should be the same. The only part that's different is this.
Is there a functional equation for this function?
No, I mean, no, you don't really expect it, or at least not in general. You don't expect it. But the point is, you don't expect it for the, on the zeta function side for an algebraic variety, you also don't really expect it there. But the point is that, you see, I mean, I'm getting ahead of myself, but I mean, the game plan for understanding Shimura varieties with bad reduction is that you would take if you take the Hasse zeta function, you take the semi-simplified version, you want to express it in terms of a product of semi-simplified automorphic L functions. And then the point is that if you know the weight monodromy conjecture, and then you will recover the actual description from this other description. In other words, the actual Hasse zeta function would be recovered once you understood the semi-simplified one if you knew these other conjectures. Of course, we don't know those conjectures, but nevertheless, we know enough about this kind of operation of replacing trace with semi-simple trace to use it in geometry. Okay, but I'm getting ahead of myself. But this is a natural object. In other words, it can, I mean, let me make some remark. You see, you don't need, how do I want to say this? All right, let me state a proposition. Okay, if we assume local Langlands correspondence plus the compatibility with these parabolic inductions, and now we have a Frobenius that we're going to make a statement over F. So we have a Frobenius in the V group. Then the statement is the following. Then the map from pi to semi-simple trace on V is a scale. This gives you a map from functions to scalars, so it should be something in the center. And so what I'm saying is that, well, just define these scalars this way. I claim that these descend to give a regular function on the space of supercuspidal supports. And that's actually kind of trivial if you assume these two things. And so what this means is that this determines a function that's a regular function on this variety of supercuspidal supports. So this thing gives a regular function, hence a function that's inside the Bernstein Center. In fact, by construction, if two representations have the same parameter, they will take the same value under this thing. So this thing will automatically be in the so-called stable Bernstein Center. Okay, so in particular, I know from abstract reasoning that I can write this as taking this thing, viewing it as a distribution. I can convolve with these things. So I get a bunch of functions in the centers of the finite level Heck algebras. Yeah?
The definition of stable Bernstein Center is spectral, right, in this setting. But you can imagine a geometric one just by looking at invariant, but stably invariant. Is it the same?
Stably invariant distributions, you mean?
Which are essentially compact.
It should be the same. But that would also be conjectural in the sense that you'd have to, I mean, it should be the same. But I don't think you can make any definition of it that doesn't require conjecture of local Langlands. Because, I mean, In other words, if you're, you can, if you knew what the Bernstein Center is, then you could, what you're saying is unconditionally define the stable Bernstein Center. I guess the problem really is just that we don't know. The very object in the Bernstein Center itself is conjectural. Anyway, but the important point is that in many cases, one can write this down in a way that's not conjectural. So for example, for GLN, suppose one did not, okay, we know the local Langlands correspondence, but suppose we didn't. We could still write down the function unconditionally that would agree with this thing in the case of GLN and in some other cases. So let me make some remarks. So the 0th remark is that, first of all, this map from V goes to this. It gives you a map from, it descends through the Grothendieck group. So it gives you a map from the representation ring to the Bernstein Center. But it's sort of not multiplicative in general. It preserves the additive structure. So it gives you a homomorphism of groups, but not of rings in general. And the second thing is, so the definition is, so to speak, unconditional in the case of GLN, where G equals GLD, and V is equal to the standard representation. That's because, well, in some sense, we know what it should be. We could evaluate these semi-simple traces based on what the expectation would come from properties of the local Langlands correspondence for GLD. But then we can just define it to be what we would calculate it to be. And that thing as itself makes sense and gives you something in the Bernstein Center. And you can use that. So in particular, so the way it goes is this. Supposing pi is it comes from the Bernstein-Zelevinsky classification. But suppose you have some kind of supercuspidals in some GLD1 cross GLDT, then and V is equal to the standard representation, then the semi-simple trace is just going to be equal to the sum over all pi's which happen to be unramified characters. And then you take that pi and you plug in the uniformizer to the R power. So the point is that the representations here, which are not unramified characters of GM, just don't appear. They don't contribute to the semi-simple trace. That's because that's essentially because of the fact that irreducible, supercuspidals correspond to irreducible representations of the Weil group, and we're sort of killing. By taking this inertia invariance, we're killing everything that's not already an unramified character. So the point is, this is what Schulze uses. So you can just take this guy as a definition, this expression on the right-hand side, and you can show it still gives you something in the Bernstein Center. And you can effectively use it to study Shimura varieties where at the prime P you have GLD. And where, I should also say, and where the representation is standard, which is one of the things that comes up for, say, the Harris-Taylor Shimura varieties. In another case where you can define it unconditionally, it's also okay if you just want to define, say, where J is a paraphoric. So in other words, we don't need any local Langlands in order to make sense of this. And the reason is, again, there's an independent way to do this. So here, this thing is a highest weight representation of the dual group. Okay? And I can, again, I want to say that there's an independent way to write down this. Well, the point is there's the center of the paraphoric Heck algebra has already been identified by Bernstein to be equal to something that's exactly like the other side of the Satake isomorphism. So you have the Weil group invariance of the group algebra over the co-character lattice of T. And inside here, you can consider a kind of monomial expression. So we're fixing mu, remember. And so we can take the average over the Weil group orbit of mu. You get some symmetric function here. And there's a function that Bernstein has constructed inside there. I'm not going to tell you the definition. It's just there is some way to define something given this monomial function, define some z mu, which is giving you an isomorphism of algebras. And if you take J to be the hyperspecial maximal compact, this is just the Satake isomorphism. So what we effectively have done is we've given a diagram. We've shown how to construct a diagram which sort of extends the Satake isomorphism and the Bernstein isomorphism there to all levels, albeit it extends it for all levels conditionally on the local Langlands conjecture unless you're in the case of GLN. And you're only interested in the one standard representation. So we get some kind of diagram of the following form. So the spherical Heck algebra is already commutative, and we know one way to think about the Satake isomorphism is it's an isomorphism between the representation ring and this algebra. And then, as I've indicated, there's the center of the Iwahori Heck algebra. That's say E inside K is an Iwahori. And then these are actually isomorphic, and by multiplying by the idempotent EK. And now Bernstein is this map here, and this triangle commutes. And as you can see, we have a whole tower of centers of deeper Heck algebras. And this multiplication is by EJ. The one coming into that is EJ. And what this does is it gives us a way to fill out this diagram. So we have V goes to, we take this Z and we convolve with IJ. So this is the arrow we've constructed. And now, so what I claim is that this has something to do with Shimura varieties, as I've been saying all along. So I want to say that a little bit more precisely. Okay, so let me just do some notation related to Shimura varieties. Shimura varieties. SHK sub p. So what this is short for the Shimura variety you would attach to, say, some global group, some Shimura datum like this, and the compact open subgroup of the adelic thing is, we're assuming it's a factor. So Kp would be a compact open inside G of Qp, which is, for all practical purposes, our G now. So now we have a global group over Q, and we take the p-adic points, and that's really our G now. So we're thinking of maybe the K upper P as being fixed, but the K lower P to be our J, and think of it as varying over different levels at P. Okay, so I also want to assume that, I don't want to state this conjecture super precisely because, we don't know exactly in what generality this should hold. It could hold extremely generally for a Hodge type or even abelian type Shimura varieties. It's practically it's been studied practically only for certain PEL type Shimura varieties. So I'm going to assume that I have a PEL type Shimura variety, and so moduli space of some kind of abelian varieties with some additional structure. And I want to assume also that I'm defined over I've got some integral model, so I'm going to assume I've over some reflex field, some ring of integers in the localized reflex field, but I even want to just assume for simplicity that this is just ZP. And again, let's assume that G, which is equal to this global G localized at QP, is split, just for simplicity. Then further data that comes from this thing is that X, well, X is some kind of family of Hodge structures. So corresponding to X, you get some kind of one parameter subgroup of the complex group. So this is, I'm going to shorten it and just call it mu. So this is a one parameter subgroup in the complex points of our group. And well, so this thing can be thought of as a weight for the dual group. Co-characters become characters on the dual torus. So we have a weight, and therefore we get some kind of highest weight irreducible representation in the representation ring G hat. And so you can probably guess where I'm going with this. So the point is, I'm claiming that there's a test function that comes into the study of Shimura varieties modulo p, and that the test function is obviously going to be given by the rule that I would take by plugging in this representation to the rule. So here's the conjecture. And afterwards I'll say what it means. And this conjecture is joint with Kottwitz. So it says that a certain power of q, I'll tell you what q is in a minute, the dimension of the Shimura variety divided by 2 times this thing here convolved with hkp to the r is a test function for the Shimura variety. Okay, so I guess I just call it here. So what does this mean? This means that this is going to be a function inside the center of the Heck algebra, which is kp to the r invariant functions on G qp to the r. So this is some unramified extension, and this is the compact open subgroup that corresponds to k sub p. So if, for example, if this was a hyperspecial downstairs, then this would be a corresponding hyperspecial subgroup upstairs. If this is a congruent subgroup, this would be a corresponding congruent subgroup upstairs, and so forth. So the point is, we're claiming that we have some kind of nice functions that are test functions. So what does it mean? Well, before I say what it, well, okay, let me say what it means. So it means that if you're doing the counting of points on a Shimura variety, in terms of computing the semi-simple trace of Frobenius, which is an analogous notion for L-adic representations as that semi-simple automorphic L function was, but I won't give you the precise definition. There's some notion of semi-simple trace on cohomology. And if you take the log of the semi-simplified Hasave zeta function with the complex number S, then this is going to be a sum of r greater than or equal to 1 of the semi-simple trace of Frobenius to the r, acting on the alternating sum of the cohomology groups some L-adic cohomology, and then you have some, again, some kind of some factors there. And so what this turns out to be, in other words, to study this function, you have to count points, count fixed points of Frobenius on here. But because of singularities, this is going to turn out to be a semi-simple trace of this operator. Maybe it's a sum over all fixed points of acting on the nearby cycles. You take the stalks of the nearby cycles. So you have to understand these quantities here. But the test function conjecture says that this should be equal, as in the usual counting points procedure, counting points on Shimura varieties, when you should write this as some kind of group theoretic data, some volume terms, and then you have some kind of orbital integral of the function. Maybe in this case, I guess it's just the characteristic function at the compact open away from P, and then a twisted orbital integral of this function at p. And what's being asserted is that this function that you can plug in here and to make this equality true is nothing other than this guy. So this is a statement about, in some sense, it's a precise statement about not. It doesn't look precise in this form because you can put many different functions here that would maintain this equality. You could change anything whose, say, orbital integrals vanish. But in this, when you restrict things to be in the center, it makes it more or less unique. But in practical terms, what it means is that it means you're saying something about the singularities and something special about the reduction modulo p of the Shimura variety, the fact that these mysterious functions actually count precisely the right things is kind of a miracle. Anyway, when the cases when it turns out to be proved, it always seemed like a miracle. Anyway, so that's what the conjecture is. The conjecture is merely that this function can be taken to be that guy. This is what I would call a global test function conjecture because it's not saying something on the face of it about these identities here. It's not saying that this is given by a certain value of this function on a certain element of the group. But there's a more precise version of this conjecture, which is called a pointwise test function conjecture, which says that you can identify these things here, these numbers, individually as the values of this thing in a suitable sense. So meaning you'd have to identify x with some kind of group theoretic element in a natural way, and then you'd plug that group theoretic element into the function. And you'd be asserting that you actually get equality. So that would be saying that these functions in the center actually calculate trace of functions on the nearby cycles. Okay, so before I go on and tell you about the evidence for this conjecture, just some examples about the setup. I mean, this in the case of modular curves, GL2, this mu. Well, here, let me just write it this way. So we have evidence. So if you have GL2 and you have a modular curve, then this thing is equal to the standard representation. Yes?
I was just wondering whether
This being the only thing that this is equal to this. This right here is equal to this, and the rest of the stuff is the same. So the S is here. Here.
Yes.
No, there's no S here. This I'm writing this term here, rewriting this, and then I'm writing this sum in this way. And there's no S anymore. Okay. So this anyway, the conjecture is true in this case. So for every J equals any level which is a congruent subgroup. So this is the result of Schulze. And more generally, if you take G equals GLD, the global data more or less being so let's consider the so-called Harris-Taylor case. So we have a globally proper Shimura variety, and the signature is this. So the co-characters is going to be, this is kind of an abused notation for co-characters, but 1 with d minus 1 zeros. In this case, also for congruent subgroups, this is also due to Schulze. Okay, and now, but historically, what came first was cases related to Parahoric level, wherein we don't need to assume much about the group. It could be, so to speak, any group of type A or C as long as the group at P is split. So if J is Parahoric, and your type A or C and G of QP is split, and the global Shimura variety doesn't have to be compact or anything, then the conjecture is true. And this is joint work with Ngo. And I should say that here the key point is that the nearby cycles are in some sense a central sheaf on the special fiber. Well, I won't say exactly what that means, but it's a la Gates-Gorey. So it's very much in the spirit of his construction of the center of the affine Heck algebra using nearby cycles. And lastly, I just want to say that in this case, we have the pointwise version is true. So a pointwise version is true. So this is a much stronger result. So it says that, so if you take an x in this Shimura variety, and let's say that it's you get a natural point inside the so-called local model. So this is for, again, Iwahori level, okay, or Parohoric level. So you get some kind of point inside in a local model, which can be embedded inside the affine flag variety for the group G. And in particular, there's a kind of, you can think of the affine flag variety as functions on there, or elements in the Iwahori Heck algebra. And what turns out to be the case is that if you take the trace of Frobenius on the nearby cycles at a point x, it's equal to the corresponding Bernstein function. So this is something in the center of the Iwahori Heck algebra for, so G over the function field. Evaluated at this x tilde times some appropriate power of q. So this is saying that these test functions actually compute traces of Frobenius on nearby cycles. And I have maybe 2 minutes to finish with just a statement of something which is due to myself and Rappaport. So this is considered a slightly deeper case. So now J is equal to pro-unipotent radical in an Iwahori subgroup. So in other words, our J is equal to our K sub P. Okay, so this is the kind of level at P. In other words, it's sometimes called the gamma 1P level structure, and the thing here would be gamma 0P level structure. And, okay, so, briefly, the conjecture is still true. But in other words, I guess I should say, what the global situation is something we call the Drinfeld case. It's like the Harris-Taylor case, except for we don't assume that the global Shimura variety is compact. It doesn't have to be. Okay, but we get something more precise, more like this pointwise version. And in fact, we get the pointwise version, which I could state in a vague way as follows. So the moduli problem for the gamma 1p level structure over the gamma 0p structure is a torsor. If you let this be the gamma 1p and this be the gamma 0p moduli problem, so this is if you let T be like the standard diagonal torus in GLD, then when you set everything up, this becomes a torsor for this group, at least generically in the generic fiber. In the special fiber, it becomes a branched covering. And along the strata, there's a natural stratification inside here given by, the so-called Kottwitz-Rappaport stratification. I don't have time to tell you what that is, but there's a natural stratification. And over each stratum, there's a kind of behavior that's constant along those strata. And although along the different strata, we pull back, say, and we get a quotient torus of T, which governs the behavior of over this given stratum. Okay. Now, if we took in the generic fiber, we took the constant sheaf here and we push forward. So let this map be pi. If we push forward the constant sheaf in the generic fiber, it decomposes as a sum over all characters of some local systems on the point here. And if we take the nearby cycles of this, it turns out that in order to understand the nearby cycles here, it's enough to just understand the nearby cycles of this, which boils down to a sum of the nearby cycles of these. So if I let the nearby cycles of those things be called Rc sub, okay. So I get some kind of interesting local systems on the generic fiber. I take the nearby cycles, I get some kind of locally constant complex on the special fiber. And I claim that we can compute exactly the trace of Frobenius on these nearby cycles. And I'll just say vaguely what we get. Here?
Yes.
Well, it's automatically a type A because we're in this Drinfeld case. But aside from that, we're not assuming anything else. I mean, there's some kind of so-called fake unitary case. So there's some kind of division algebra over a quadratic imaginary extension with an involution of the second type. And you construct a kind of fake unitary group from that. So it's type A. But so at P, we assume it splits, but that's actually not going to be necessary. That's not really necessary in the method of the proof. So what we get is that the trace of, so here's the theorem. The main theorem of this work with Rappaport is that the trace of Frobenius on this nearby cycles associated to the character at a point x. So x is a point in, say, if p to the r points, but maybe it's inside this given stratum w. We can always assume it's in some stratum indexed by some element w. I don't have time to tell you what the w's are, but there are some elements in the extended affine vowel group. Anyway, you have some, I mean, I'm going to write it this way, but here, so the key point is that this this function here is something in the center of a Heck algebra that is on this group, which is almost an Ewell-Horry Heck algebra, but it transforms on the right and the left according to some character of the Ewell-Horry, and that character comes from the chi. And this is some element in this quotient torus. I mean, I should say it's something in a torus which maps to a particular thing in the quotient torus. But it's sort of irrelevant. I mean, it's not irrelevant at all, but it's sort of, I don't have time to explain it, but it's just some group theoretic thing that you can attach to the element x. And this is also a group theoretic thing, namely the stratum. Okay? And the point is that we find these functions that happen to be in the centers of these Heck algebras, and they're some explicit things, so we compute them explicitly in the same way that you can compute functions in the center of an Ewell-Horry Heck algebra a la Bernstein. So we give kind of corresponding, even more explicit descriptions of these functions. And the point is that a priori, when you study these things, you get a function that is just inside the Heck algebra, not inside the center. And it turns out that we can use Heck algebra isomorphisms to identify, to show what these things are. So we use the Heck algebra isomorphisms of Roche and Goldstein and Morris to identify and prove the centrality of these functions. And so I should also, just in closing, mention that Schulz's stuff, which works for arbitrary congruent subgroups, it doesn't seem possible to get some kind of pointwise result for it. And this has something to do with the difference between the general situation and depth 0. So for depth 0 situations, we expect that this situation should generalize. Okay, that's it.
Thank you.